All right, good morning, everybody. Let's start by a quick check. If you can hear my voice, please raise your hand. Yeah, you can go ahead and lower your hand. Now, let's see. Some of you have been asking for information on uh, just an example on Thevenin and Norton equivalent. So what I did was to go ahead and post some notes, okay, on 108 section. Let me make sure. Yes, 108 section on Thevenin and Norton. Okay, I'm also going to show you one example um, of doing Thevenin and Norton equivalent circuits. Begin. Okay, so in this, this is basically a review of Engineering 17 that you should have done in your previous classes. So this notes is right out of that. If you scroll down all the way, okay, there is this node voltage method, there is mesh current method, so on and so forth that we use to um, solve for different circuits. Now, further down, about 2/3 of way down, okay, there is source transformations, and then after source transformations, there is this Norton and Thevenin equivalent circuit. It's a review of what you should have done in Engineering 17. Okay, so they talk about how a Norton equivalent circuit. Okay, so the idea is that from the perspective of a load, okay, let's say I have a black box. I don't know what is sitting in there. Okay, if I can reduce and understand the behavior of all of this circuit, um, and if I can model it using one voltage source in series with a resistance, then from the perspective of the load, we know just about everything that we need to know about its terminal behavior, about the terminal behavior of this black box. Okay, so reducing a circuit into a voltage source in series with a resistance from a terminal behavior perspective. That's the idea of Thevenin's equivalent. Okay, there's a simple example here. When you're asked to find the Thevenin equivalent, there are two things that we need to find. Okay, the first thing you need to do is open circuit voltage. So let's say these are the two terminals across which you connect the load. Okay, the first thing you need to do is to open circuit the load, open circuit this, and find the open circuit voltage. So that is tantamount, that is equivalent to finding the voltage across these two nodes. Okay, across these two nodes. That's the idea. Um, Across node X and node Y. Okay, that's the idea, open circuit voltage. Because it is open circuit, there is no current flowing in this 4 ohm resistance. Okay, and that's the reason why we are not considering the voltage drop across this card. There is no current flowing in. What's the current flowing into an open circuit? Infinite resistance, zero current. So there is no voltage drop across this resistance. Therefore, the open circuit voltage is V across X and Y. Okay, because V dropped across the 4 ohm resistance is zero because it is open circuit. Okay, so that's the first part of the equation that we need to find, V open circuit. Okay, so in order to find the open circuit, they use node analysis, node voltage method. So this is considered to be V 3 amperes. So the setup node equations here. Okay, the current flowing in here is 3 amperes. Okay, the current flowing through this resistance is V3 amperes minus 25 volts, which is this guy, over 25 or over 5 ohms. Okay, so the idea is summing all the currents at one particular node, at this node, which is the same as that node. Okay, and then there is a current flowing in this guy. Okay, if you consider this to be ground, voltage 3 amperes minus 0 by 20 ohms. So there are 3 branches of currents. Let me color code them carefully. So let's see, I'm going to call this 3 voltage 3 amperes. That's the voltage at that node. Okay, we're going to consider this as a reference voltage. We'll get away by calling this ground. It's a simplification, and this voltage, so there are 3 branch currents here. There is one current flowing in this direction that is shown here. Okay, and then there is this current shown here, and then there is the current here coming into the 3 amperes current. So you sum all the currents in there, that should equal 0. From that, you can calculate V3 amperes, the voltage at this node, this guy, to be 32 volts. So that's the first step. Remember, the idea was to find the V open circuit, which is exactly the same as V3 amperes. Okay, that guy. Once you find that, the next step is to find the Thevenin resistance. Okay, so this is step 1.
Professor,
Yes,
can you explain one more time how do we get equations?
the equations here.
Yes.
Okay,
What's
the
your
equation
circuit?
here. Sure. Let me write them out here. So consider this node, that node right there. Okay, what's the voltage at that node? That's considered to be 3 amperes, right?
Yes.
That's V3 amperes. So I'm going to set up KCL at node, I'll call this at node X. Okay, so the amount of current leaving is equals to the amount of current entering. So the amount of current entering is 3 amperes, right? That is
Yes.
equals to the amount of current leaving. So this is also voltage 3 amperes by 20 ohms. That's the current flowing in the branch downwards. You with me?
Okay.
Plus
Yes.
the voltage difference between this node and this node, that's the voltage dropped across that resistance. So V3 amperes minus 25 volts is the voltage dropped across the 5 ohm resistance divided by 5 ohms will give us the current in that direction. So all I'm doing is KCL at that node X. Sum of the current leaving is that guy. Some of the current entering is that guy. So the rest is all algebraic manipulation to give us V3 amperes to be 32 volt. Does that make sense?
Yes. Like, why is it like minus 25?
Yeah. So the current, it is assumed that the idea is this is at a positive potential, this is at a negative potential, right? Current flows from high potential to low potential. Arbitrarily, I chose the value to be this guy. So this is ground, assuming this to be ground. This voltage source, don't forget this guy, that puts up a voltage of 25 over here. So this voltage minus this voltage is the voltage dropped across this resistance.
Okay.
Does that make sense?
Yes.
Okay, so that's the idea. The reason I chose negative 25 volts there is because of the voltage source here. Okay, so I set up KCL at node X so as to sum all the currents entering and all the currents leaving, equate them. So I get a value of V 3 amperes, that node voltage to be 3 amperes, which is the same as the V open circuit that I want. Okay, that's 3 amperes. That's step one. Okay, that is step number one. Okay, let's see step number two. Step number two is find the Thevenin resistance. Finding the Thevenin resistance is to temporarily ignore all the voltage and current sources, deactivate. I mentioned something like this in the last class. Okay, short circuit voltage sources and set current sources, open circuit current sources. Okay, so there are two things that we need to do. Any independent voltage sources are short circuited. Okay, any independent current sources are open circuited. Okay, that's exactly what I'm doing here. I'm going to open circuit this guy, meaning I'm going to do it like so. I'm going to open circuit that current source. Okay, and then I'm going to have to short circuit this short circuit that voltage source. Okay, the result is going to be something like that, looks like this. Okay, I short circuited the voltage source over there. The current source is open circuited here. So I'm left with a parallel combination of 5 and 20 in series with 4, which gives me a resistance of 8 ohms. Does that make sense? So this is 20 in parallel with 5 ohms will give me 4 more. So I have 4 ohms in series with 4 ohms. Okay, across A and B. That gives me RAB. Now I have V Thevenin, which is found out to be 32 volts, and R Thevenin, which is just found out to be 8 ohms. Now I can write the Thevenin equivalent of all of this circuit. So all of this circuit is simply equivalent to 132 volt resistance. Dang it. 32 volt resistance, 32 volt source in series with a resistance of 8 ohms. So that's the idea of Thevenin equivalent, finding the open circuit voltage and the Thevenin resistance. How do you find the Thevenin resistance? You simply deactivate the independent current and voltage sources. Okay, and I welcome you to go through this. There are some more examples. There are some examples of Norton equivalent calculation as well. So even for that, you have to find the Thevenin equivalent resistance, so on and so forth. Okay. So here is one example on how to do the Thevenin equivalent. There are two steps. You simply have to find the open circuit voltage, VAB, and R Thevenin. This is also called V Thevenin. Find V Thevenin and R Thevenin.
So,
Yeah, let me go back. Did you have a question about that?
yeah, like, is there any like particular formula to find the voltage, like Thevenin voltage? Like, I was
No, this is the general procedure that you want to follow.
okay.
Okay. So look at this example, do a few of these examples, and then it will become second nature to you.
Okay.
Okay. There's no particular formula. Okay. All right, let's continue from where we left off. This is what we did in the last class. We started looking at operational amplifier. Okay, the advantage of operational amplifier is that it has a really large gain, which can be used to trade off for something else. Okay, we can you can gain some bandwidth in return for gain, the extremely high gain. You can trade that off for high gain. Now, they're most often used in negative feedback configuration, which makes everything better. Okay, negative feedback configuration is shown here. Okay, negative feedback configuration is shown here, where you feed a part of the output, a fraction of the output back into the input. Okay, and then you amplify the difference signal. Okay, and you can see this guy somehow when you're calculating the difference and amplifying that difference. Okay, and that is the underlying idea of an operational amplifier. Look at the difference and amplify the difference. That's what I want to do. Okay, so we define open loop gain, which is from xi to x0. And then we also define the closed loop gain, which is much smaller, xs to x0. And then we define the feedback factor, which is a fraction of xs over x0, the amount of signal fed back compared to the amount that's the output. Okay, so there are different types of gains. Okay, okay, so we looked at the key concepts that are related to negative feedback. The main fundamental idea was that if I use a gain that is extremely large, the open loop gain, if a open loop gain is really, really large, then the closed loop gain AF becomes 1 over beta, completely independent of the open loop gain A. Okay, many times we find that the open loop gain A varies with process, voltage, and temperature. It's all over the place. It's really hard to keep a constant gain for A. But the idea is that if you keep it relatively extremely large, then this factor A is equals to 1 plus A beta. Uh, you can ignore the term 1 here, okay? And then the overall gain AF becomes 1 over beta, okay? So independent of the open loop gain. That's the idea. And then we looked at the symbols for operational amplifiers. Even though I'm not showing them here, even though I'm not showing them here, these are understood. The power supply is VCC, and the negative power supply, negative VEE. Okay, these are definitely there. There is no amplifier that can work without these power supplies. It's just that they're understood, not explicitly shown. Okay. Now, there are some the output, V output resist, the relationship between output and input has been defined to be V output is an amplified version of the difference between the inputs. This is what we saw in the last class. Okay, if there are two inputs that I am applying, uh, then the difference between them is shown as the output after an amplification. Okay. Now, there are certain assumptions that I talked about when it comes to ideal op amps. The first assumption is that the open loop gain is infinity, which gives me the conclusion, the result, that there is a short between the two terminals. There's a virtual short. Whatever voltage shows up on one invariably shows up on the other in a closed loop configuration. Open loop gain is infinity is the assumption one. Okay. The second assumption is about the bandwidth. The third assumption that I often use in um, calculations in problems is that the input resistance is zero, the amount of current flowing in is zero. And then, of course, the fourth assumption is that the output resistance is zero. The input resistance is infinity, meaning that the current flowing in is zero. The other assumption is that the um, common mode signals experience a gain of zero, something we discussed in the last class. Okay, now the same signal V1 is shown here by algebraic manipulation, by manipulating it algebraically to be the sum of, let's say, to be the sum of a common mode signal plus a plus a differential mode signal. Okay. Similarly, this guy, the same voltage here, can be shown as a common mode signal minus some differential plus some differential signal. So here is the idea. So this guy V1 is expressed as V input common mode minus V input differential mode over 2. Look at the polarity here, plus and minus. Similarly, V input V2 can be expressed, so this is V1. V2 can be expressed as V input common mode minus plus V input differential mode over 2. Okay, so pay attention to the polarity, negative and plus. So this guy is same as V1. This guy is same as V2. Okay, these are definitions that we looked at in the last class, where V input differential mode is defined as the difference between these two terminals. V input common mode is defined as the average between these two terminals. Okay. Okay. Now let's look at some simple applications of um, amplifiers. Okay, let us look at some applications of amplifiers. Just give me 1 second. Okay. Okay. So there are a bunch of applications uh, for inverting amplifier, for an operational amplifier, and I'm going to show you a general approach that we follow when it comes to calculating the output as a function of the input. Okay. So all that is happening here is, let's try to understand the basic configuration here. There is the output. A part of that output is tied back into the negative terminal. Okay, so this should ring a bell. This should ring a bell when you see a part of the output is fed back into the subtraction terminal of a closed loop amplifier. Negative feedback configuration. So this is the idea of negative feedback. I feed a part of the output back into the input side on the negative input terminal side. Okay, so there is a resistance paid here, R1 and R2. Okay, and then the input is applied. Input is applied to the negative terminal through R1. Okay, so let's try to solve this. Let's try to get a value for how V out is going to vary with respect to V in. Okay, so I'm going to do that and then do that on calculation for this problem, and then for the rest I'm going to show you how to do it yourself. Okay, so there is that voltage that I'm applying. This is called an inverting amplifier. Okay, because the input is applied to the negative terminal. Input is applied to the negative terminal, which is V in, VI. Okay, V output or the V positive terminal, the second terminal of the two is tried to ground. Okay, output voltage is measured across these two V output. This is R1, this is R2. So let's do the generic approach of trying to analyze this circuit. The first step, the very first step that we do is to notice that there is a virtual short. Okay, there is a virtual short between the terminals 2 and 1. And why is that virtual short coming from? Virtual short is coming from the fact that the open loop gain is infinity. Remember? So the idea was that because the open loop gain was infinity, the voltage between the terminals plus and minus is zero. Okay, that was the first assumption. So whatever voltage is applied on one terminal shows up on the other terminal. So there is a virtual short between these two terminals. So this guy, number one, also behaves like a ground. So that's the idea of virtual ground. Okay, that's the idea of a virtual ground. So now I know this potential, this voltage is at 0 volts. Okay, so what I'm going to do is I'll try to find the current. Okay, so I'll try to find the current that's flowing through each of these resistances. So there is I1 current flowing in here. There is current I2 flowing in here. Okay. Now let's say there is some small teeny tiny current I3 flowing in there. What would be the value of I3? I3 would be 0. Remember, that is because current flowing into the OpAmp is 0. So Rin is assumed to be infinity. So let me go back there. Okay. So pay attention to this guy. Rin is infinity. So the current flowing in is 0. Okay. So that's the assumption. Assumption number 3, ideal OpAmp assumption number 3. Okay. So ideal OpAmp assumption number 1 is applied here, virtual short. The first step is to identify that the ground terminal on number 2 shows up on number 1 as well. The second assumption is that the current flowing in to OpAmp is 0. So that gives me that leads me to this idea that I1, all the current flowing in R1 should flow out through R2. Okay, that's the idea. That
Um, Professor, I have a question.
Now, I2, the current flowing through the resistance I2 is going to be the voltage on the left of I2, which is 0, minus voltage on the right of R2, which is V out, over the resistance of that guy, R2. Okay, so implies I2 equals to the current flowing is V output over R2. Okay, and we want them to be equal. The idea is that both of these are equal, and that's the fundamental assumption. Okay, Vi over R1 equals to negative V out over R2 implies V out equals to negative R2 over R1 times V in. Okay, so this is the idea of inverting amplifier. V output is negative R2 over R1 times V in. Okay, the idea is if this is your V in, okay, V output is going to be an amplified version and an inverted version. So this is V output, this is V input. That is what the negative term over there means. So all I have done is applied two assumptions. The first assumption is that whatever voltage is applied at one terminal shows up at the other terminal. That's one assumption. The second assumption is that all the current flowing in one branch, in one resistance, has to go through the other one. Does that make sense?
I have a question, Professor.
Yes.
So the graph that you make, a little graph for the V in and V out,
Yes.
could we represent V out as a shifted graph, like not inverted sign, but the same sign graph, but shifted over?
Well, that is exactly what is happening as a matter of fact. I'll show you. Wait. Okay. Let's say this is my sine wave. What you are asking is that I have an input sine wave. Pardon, I'm not the world's best artist. So what is happening here in the output is exactly that it is shifted. I'll do this. Hold on 1 minute. Okay. So what exactly is happening is, okay, that's shifting by okay. So shifting by 180 degrees is exactly the same as inverted. Okay, that's what I'm trying to drive, I guess. So let's say that's my input. Okay, now the output is, that's the output that is shifted by 180 degrees. Okay, it is shifted by 180 degrees. So the idea is that it appears inverted. So if you forget this part, okay, forget this part of the circuit, okay, it is all I have done is shifting a sine wave by 180 degrees, it appears inverted. So your question is, can I draw this circuit as inverted, as a shifted sine wave instead of an inverted circuit? Well, they're both the same. If you're shifting it, that answer your question?
Yes, thank you.
Okay, yeah.
Um,
So in addition to the shift here, there's also an amplification. Yeah, go ahead.
I have a question like, what is like open loop gain and closed loop gain?
Yeah. The gain of this guy, the gain of this amplifier, AV, that's the open loop gain. Okay, it can be a really large number. Okay, but that is not showing up here. The gain here of this circuit, it's in a feedback configuration.
Mm-hmm.
Okay, the gain in a feedback configuration here in this case is V out over V in, which is negative R2. over R1. That's the closed loop gain. Okay, let me close loop gain. This is closed loop gain or loop gain, and this guy is open loop gain.
Okay. So like whenever we have a feedback register, it is closed loop gain.
When we have a feedback circuit, it goes back to the idea that I discussed earlier. When I have a feedback circuit, okay, something like this, okay, when I have a feedback circuit, as long as the open loop gain is really, really large, when the open loop gain is really large, then the closed loop gain, you don't find open loop gain in the equation. There's only the feedback factor. Okay, so that's the idea.
Okay.
We'll talk about it more shortly. Does that make sense?
Yes.
Okay. So that's the idea of inverting amplifier. So let me do one more problem here, the non-inverting amplifier. Let's do the inverting amplifier. Let's quickly recap the inverting amplifier here. This is what we did. There is a negative terminal, there is a positive terminal. The positive terminal is tied to ground. The negative terminal, in the negative terminal, I applied a voltage Vn. And that's the reason why it behaves like an inverting amplifier, because I'm applying input at the negative side, at the negative terminal. Okay, so R1, R2, V out. Okay, plus minus V out. Okay, so the idea is that V output is negative R2 over R1 times V in. Okay, that's the idea. And then remember the important thing I want you to notice is that the input voltage V in is applied on the negative terminal. Okay, on the negative terminal, and then V positive is tied to ground. Okay, let's see what is happening on the non-inverting amplifier. For the non-inverting amplifier, the exact opposite is happening. The input is tied to the positive terminal, okay, and the this guy, the resistance R1 is tied to ground. Okay, so the first assumption is that there's a virtual short between these two, so that makes this guy equal to the same exact voltage right here. So this will be a VI as well. Does that make sense? Because of virtual short. The very first step is that this voltage is virtual short. Okay, you can think of a wire connecting these two. So whatever voltage is applied on one shows up on the other as well. That's the idea of virtual short. So now the next step is to equate the currents. Okay, R1, step one is virtual short. That's step one. Step two is to realize that the amount of current that is coming from R2 will all flow through R1.
But
Question?
Professor, like at that point, isn't it a virtual ground? Like, isn't it voltage is zero over there?
Virtual ground, virtual ground is a special case of virtual short. Okay, if this guy is ground, then this will also act like ground, not a real ground, but like a virtual ground. But in reality, what is happening is this guy is a voltage. So this node also behaves. So this guy is a voltage V1. That also behaves like a voltage V1. Okay, so if this is a ground, like I tied earlier I had this guy tied to ground, right? So
Okay.
this behaves as a ground as well. Then we call it a virtual ground.
Okay.
Okay, virtual ground is a special case of virtual short.
Okay, so not every time it's virtual ground.
Correct. A virtual short can act as a virtual ground if one of the nodes is a ground.
Okay.
Does that make sense?
Yes.
So the second step is to realize that the current flowing through R2 should all go through R1. Now we express the currents for, now we get the value for currents I1. I1 is what? this voltage V1 minus 0 over R1. That should be equal to the current flowing in through the resistance R2, this current, okay, which is V out minus Vm, V out. Remember, this guy is V out, this guy is Vi, because that guy is Vi, right? So this is Vi. So if you want to find the current through this resistance, that will be V output minus V input over R2. Okay, so that's the idea. So only two steps. The way there are only two steps to solving any op-amp problem. The first step is virtual short. Okay, step one, virtual short. Okay, whatever voltage is applied on one node shows up on the other node. That's step one. The step two, current flowing in I of an op-amp is 0. Therefore, all the current has to be routed around the op-amp. The current flowing in this branch should equal the current flowing in this branch, because the current going into the op-amp itself is 0. Okay, application of these two principles is all there is to op-amp solutions. Okay, so that's exactly what I have done. This guy is I1, this guy is I2. So I1 equals to I2, I1 equals to I2, because there is no current flowing into the op-amp. Okay, once I rearrange these equations, all I see is V output over V input is 1 plus R2 over R1. Okay, V output is V input times 1 plus R2 over R1. That's all there is to. So if I were to apply this as my input, okay, the output would appear like so, an amplified version, but in phase with that signal. Does that make sense? So non-inverting amplifier, because the input and output are in phase.
Professor, like there's a little bit of confusion. Like if the voltages are equal at both the terminals, so isn't it gonna be cancel each out? Like what it gonna amplify?
In the feedback configuration, what happens is the assumption is coming from the fact that AV, the open loop gain, is infinity. Okay, so what is happening is we are setting up voltages in such a manner that the resistance ladder here, the resistance network here, R1 and R2, split the voltages carefully, split the voltages in a manner that is advantageous to us. Okay, so that's the idea. Now, so this is a non-inverting amplifier. The main difference between non-inverting and inverting amplifier is that, let me clean this up a bit. Okay, the main difference between non-inverting and inverting amplifier is that the input is applied to the positive terminal in a non-inverting amplifier, and the input is applied to the negative terminal on the inverting amplifier. Okay, in the non-inverting amplifier, the output voltage is 1 plus R2 over R1 times input voltage. In the inverting amplifier, the output is negative R2 over R1 times the input. Okay, that's the idea of non-inverting amplifier. Okay, so let's quickly take a look at the idea of a non-inverting amplifier as a feedback amplifier. Okay, a non-inverting amplifier is a feedback amplifier. So I'm trying to draw parallels here between this guy, okay, open loop gain A. There is a feedback factor beta. There is a summation. So this is a feedback idea, right? So there is V of S, there is a feedback VF, there is a beta, there is V output, okay? There is VF over there, okay? So the idea is a non-inverting amplifier in feedback configuration behaves pretty much like a negative feedback configuration with a feedback factor of 1 plus R2 over R1. Okay, so remember this guy. This is exactly the same. This is exactly identical to this guy. Okay, that's the voltage over there. Now, the idea is that there's a negative feedback in here. There's a negative feedback to resistance R1 and R2, which forms the beta component. Okay, which forms the beta component of this guy. Okay, that's the idea of the beta component, and VF here is pretty similar to the fraction of the voltage that is left over there. Okay, the feedback factor beta is defined as VF over V naught, which is the voltage division here. Remember, the voltage here is the voltage across the R1 resistance. So the voltage division is R1 by R1 plus R2 times V out. Okay, so VF over V out, the fraction is R1 by R1 plus R2. Therefore, we have a a closed loop gain AF of A by 1 plus beta, which is approximately 1 over beta, which is the same as R1 plus R2 by R1. So this comes out to be, so if you do the math, if you rearrange this equation, you can see that this fraction 1 over, this fraction 1 plus R2 over R1 is actually 1 over beta, where beta is defined as R1 by R1 plus R2. Okay, so we can see that a non-inverting amplifier is behaving like a negative feedback circuit with a beta of R1 by R1 plus R2. Okay, so that's the idea. So we looked at two applications of op-amps. The first one is inverting amplifier. The second one is non-inverting amplifier. In the inverting amplifier, V output is negative R2 over R1 times V input. Okay. In the non-inverting amplifier, V output is 1 plus R2 over R1 times V input. Okay. That's the idea in non-inverting amplifier and in inverting and non-inverting amplifiers. The third application that we are going to look at is unity gain buffer. Okay, as the name indicates, the gain of this guy is 1. Okay, I have taken an op-amp, tied the output back into the input. Okay, into the negative terminal. Okay, you can clearly see that R2 is 0. There's no resistance R2 over here, and R1 is infinity. Okay, R1 is infinity. So as a matter of fact, what we see is that all of this term goes to 0. Therefore, I'm left with a voltage gain of 1. Okay, so whatever is applied at the output will show up as the input. Okay, so that's the whatever is applied as the input will show up as the output. So this is unity gain. Unity gain buffer is a special case of non-inverting amplifier with a voltage gain of 1. So if R2 is 0 and R1 is infinity, R1 is open circuit. Therefore, it's a infinity. So it's a unity gain buffer. There are applications where we need to use amplifiers with just a gain of 1. Okay. One of those we saw in the previous class where we had to match the impedances to our taste. Okay, so unity gain buffer. So 3 applications of OpAmp that we saw so far. Okay, the 3 applications of the operational amplifiers that we saw are inverting amplifier, where the gain is negative R2 over R1. Okay, a non-inverting amplifier, where the gain is 1 plus R2 over R1 times V input, that's V output, where there's a unity gain buffer, where the voltage gain, the closed loop voltage gain is 1. Okay, all of these are based on 2 principles. The first thing is virtual short. The second one is I is 0 because our input is infinity. Okay, so all the current is routed around the operational amplifier, setting up voltages and currents that give us the behavior that we analyzed here. Okay, so that's the idea of operational amplifiers used as unity gain buffers, non-inverting amplifiers, and inverting amplifiers. Okay, so the next application is inverting summing amplifiers. Okay, inverting summing amplifiers. So let me point to you really quickly that this is a special case. This is an extension really of what we saw earlier, an inverting amplifier. Okay, so remember the inverting amplifier. Let me go back there. Let me show you the inverting amplifier really quickly. Here is the inverting amplifier. Okay, see what is going on. One positive terminal is tied to ground. Okay, the negative terminal, to the negative terminal, I apply a voltage through some resistance R1, and then there is a feedback resistance R2. Okay, now I'm going to show you an extended version of this. Okay, before we see the extended version, let me show you how exactly they are the same in its simplified version. So see, take a look at this. The positive terminal is tied to ground, sure enough, and the voltage V1 is applied to the negative terminal through resistance R1. So there is a resistance, feedback resistance RF. As you can see, if you look at the output here and momentarily forget all of this, okay, the output looks pretty similar to what we have seen before. V output is negative RF over R1 times V1. So this is what I would expect out of one voltage driving a negative terminal through a resistance R1 and a feedback resistance R2. This is an inverting configuration. The same can be extended to include more than one inputs. What if I included N resistances in parallel through voltage V2 all the way through voltage Vn. Okay, then the output simply is an addition of all of those, a superposition of all of those. Okay, so RF over V1 times R1 corresponds to that guy. Then there is let's see, RF over V2 over R2 corresponds to this guy. Okay, so similarly, then there is a RF over Vn times Rn corresponds to, oops, I want to do that using this guy. RF over Vn times corresponds to this guy. So if I have more than one input going into an inverting amplifier, then it behaves as an inverting summing amplifier, because the fundamental idea is, if you look at one node, if you look at a node, this guy, okay, at that node, what happens is all the currents flowing into that node add up here to form I. Then that I is going to be routed through RF, okay? Because the amount of current flowing into the op-amp is 0. Does that make sense? So inverting summing amplifier is simply an extension case of an inverting amplifier. Does that make sense?
So, like we can have the same case for the non-inverting too.
Yeah. Yeah. Okay. We can have the similar case for non-inverting amplifier as well, non-inverting summing amplifier. Okay, where there is more than one. Okay, when there's more than one inputs tying into the positive terminal. Okay, and then there is the all familiar negative feedback loop. We'll come back to that. Okay, we'll talk about that shortly. Okay, so here is a summing amplifier with positive and negative inputs. So pay attention to this. The idea is that V output is a negative sum of all of these inputs. Okay, what if I wanted to have some terminals add and some terminals subtract? Well, I can do that by having two amplifier stages, two stages of amplifiers. Okay, one, both of these are inverting amplifiers. See, what I have done is I have cascaded two stages of inverting amplifiers. Okay, inverting amplifiers, multiple amplifier stages can also be cascaded to provide for both positive and negative gains. Okay, so when I have two negative inverting amplifiers cascaded back to back, the product is going to be positive. Okay, the output signal from the first stage sees an additional gain. So the output signal here, that sees an additional gain of negative RC over RB. Okay, so whatever is the voltage output of stage 1 here, that is multiplied by negative RC over RB. If you remember, the gain of the first stage is really negative RA over R1, okay, for V1, okay, R2 for V2. So the product of two negatives is going to give us an overall positive. So we can mix and match these guys, V1 and V2 are multiplied by two gain stages, okay? There's a gain from here to here, and there's a gain from here to here. This gain is negative, and this gain is negative. So V1 and V2 have a positive overall gain. But pay attention to this, okay? V3 and V4, well, they're only going to go through one negative gain stage. So V3 and V4 have an overall negative gain, okay? So the idea is that I can selectively apply I can selectively choose which inputs are are scaled with a positive gain, and I can apply the inverting inputs at the second stage. Okay, so that way I can mix and match summing amplifier with both positive and negative inputs. So this comes at a cost that I have to use two operational amplifiers. Okay, that's the problem. Okay, so V1 and V2 experience a positive gain because they are multiplied by two negative gains. Okay, there's only one gain. Two negative gain stages on the other hand. Okay, so that's the idea of summing amplifiers with positive and negative input terminals. Okay, here is a non-inverting summing amplifier, like I discussed earlier. Non-inverting summing amplifier. Let's see how this is a non-inverting case. Look at V1. The input is applied to the positive terminal. So let me do what I did earlier. Let me analyze this in the absence of the other branch. Okay, in the absence of another branch, just looking like so. Okay, so if you look at this, so this is V1 applied here. So if you look at this and compare this to the non-inverting amplifier, let's try to look at the non-inverting amplifier here really quickly. This is the non-inverting amplifier. The input is applied to the positive terminal. The feedback is applied to the negative terminal through R1 and R2. Okay, through R2, that is where the feedback is coming from. But then R1 is there before it is tied to ground. Okay, so let's see if the exact same configuration is shown here or not. Okay, and then we know how the gain appears. Gain V out over V in for a non-inverting case is 1 plus R2 over R1. Okay, so let's apply the exact same thing here as well. See, the positive voltage V in 1, the input voltage is applied to the positive terminal exactly as in a non-inverting case, exactly as in the case of a non-inverting amplifier. And then the feedback is tied to the negative terminal here through resistance R2, and there is another resistance R1 over here. Okay, what is the gain of this guy? The gain of this guy, V out over V1 is 1 plus R2 over R1. Okay, because that is 1 plus R2 over R1. Okay, this is a non-inverted case. Sure enough, I have that 1 plus R2 over R1 gain. Okay, so in addition to that, what if I have more than one branches? Okay, what if I have more than one inputs? Let's say I have another input here. Okay, let's say I have another input, this guy here. Okay, and I have another input here. Okay, the only difference though is if you pay attention, earlier this guy was tied to the voltage directly, V1, but in this case I'm branching it, I'm putting it through another resistance R1. So when I come to do the superposition theorem with V1, okay, when I do the superposition, one of the power sources, one of the voltages is going to go to ground, and the voltage that is left here will be the fraction 3k over 2k plus 3k times 1. Okay, so let me draw that out here. I'll probably, why don't I draw this out here? Let's see, add page. Just give me 1 second. Okay, non-inverting summing amplifier. I have one OpAmp. Okay, this is 9K. This is 1K tied to ground. Okay, and then there is a 2 kilo ohm resistance through which V1 is applied. Okay, 2 kilo ohms resistance through which V1 is applied. And then there is a 3 kilo ohm resistance through which V2 is applied. Okay, what is the overall voltage here? That'll be exactly same as here as well. Okay, whatever voltage shows up here shows up there as well. So for a minute, let me do the superposition by tying one to ground, one source to ground. I'm going to evaluate the input voltage independently of the two inputs, each input independently of the other. So I'm applying a voltage V1 over here, okay? And then there is a resistance R3, 3 kilo ohms over here, okay? Now, the voltage here is going to be the voltage division between 3 kilo ohms and 2 kilo ohms, 2k ohms plus 3 kilo ohms times V1. That will be the voltage that shows up here. Okay. Now let's not forget the other source. There is another source here, V2 as well. 3 kilo ohms, V2. So in order to calculate the effect of V2 at this node, I have to apply superposition. So I tie one of the other input to ground and do the voltage division, which comes out to 2 kilo ohms over 3 kilo ohms plus 2 kilo ohms times V2. The sum of these two, okay, the sum of these two is the overall input voltage that is seen at this node. Okay, the sum of these two superposition is seen at that node, which is amplified by the 1 plus R2 over R1. Okay, 1 plus R2 over R1. Sure enough, that's exactly what we see. The overall input voltage is a voltage division of V1. A part of the voltage is appearing there, and a voltage division of V2. A fraction of V2 is appearing over there. All of that is multiplied by the gain. Okay, so this is the gain. This is the input voltage. Okay, so what I have here is V1 plus V2. Each of those are scaled. Okay, so the idea is it is a non-inverting amplifier. It's a summing amplifier. If I apply V1 over here, V2 over here, the overall output is going to be V1 multiplied by 6 plus V2 multiplied by 4. There is some amplification factor for V1 and some amplification factor for V2. Does that make sense? Questions, please. Okay. So that's the idea of non-inverting summing amplifier. So far we looked at a bunch of amplifiers. We looked at an inverting amplifier, a non-inverting amplifier, a unity gain buffer, an inverting summing amplifier, and a non-inverting summing amplifier. Okay. Then now we can look at difference amplifiers that amplify the difference between the input terminals. But what I want to do is I want to take a break here. There's the idea of common mode rejection ratio. This is what we will continue talking about in the next class. Okay, common mode rejection ratio is a measure of how well our differential amplifier can amplify the difference between two input signals and reject common mode signals. Okay, that's the idea of common mode rejection ratio. Then we'll come back to talk about instrumentation amplifiers. Okay, and then a few varieties of those. In the next class, we are going to see how we can implement integrators and differentiators using op-amps. Okay, and in addition to the active low-pass filters, we'll look at some non-ideal effects of op-amps. Okay, non-ideal effects. We made some assumptions about the open loop gain, which is infinity. The current flowing in is zero. So we'll revisit those assumptions and see how it can differ, how our circuit can differ from those uh, ideal assumptions. Okay, so these are some of the things that I want to differ for the next class. Questions, please. What questions do you have at this time?
So our one midterm is on Thursday, right?
Midterm is on Thursday. Correct. The beef of your learning is going to come from the videos that Dr. Perry Heatley posted online. So all of those, he talks about all of these slides and all of these applications in a very methodical manner. So I invite you to go through those videos carefully. My lecture is only meant to be an addition to what is already available there. So it may not be possible for me to cover all the material in the class for the midterm, but that's not even the idea. This is a flipped classroom style. All the material for the classes exam is already available on Moodle as video lectures. So chapter 1 and chapter 2, signals and amplifiers and operational amplifiers, it will be fully covered for the midterm on Thursday, the day after tomorrow. And I'm only going to discuss some topics again in the interest of completeness, but not necessarily all the material. Okay, so I have a question in the chat that says, any pre-lab calculations or simulations for lab 2? There is one circuit with a diode. Okay, there is one circuit with a diode for the second lab. That's the only thing that you need to do the simulations on. Okay, the transient analysis for a circuit with a diode, you apply a triangular wave and see how the upper part of the triangular wave is passed and the lower part of the triangular wave is cut off by the diode. Okay, there's another question. How will the midterm be? The midterm will all be online. You have to log in to the same um, class section using Zoom and turn your camera on. And while the camera is going, I give you the passcode to start taking the midterm exam. It begins during the class time. Okay, and it'll be, you will have 3 attempts to take the exam. So the best of the 3 will be taken. The time will still be the same. The time will still be the same. And if you want to scrap your first attempt and take a second attempt, that's fine. You'll all have your cameras on during the midterm time. Yes.
I have question
Yes.
about the the second lab. So tomorrow we will have a lab, I think,
Yes.
but we will do the demonstration tomorrow or next week.
Tomorrow.
Okay. Thank you.
Is there any practice midterm available?
Well, there are quizzes at the, let me see. Let me go to the Moodle site, right? All the way down here. If you go, there is practice quizzes and exams. Okay, so that will be practice midterm exam 1, practice midterm exam 2, practice. So there is some practice posted on there.
Okay.
Okay. About a formula sheet, it's fine with me if you want to have a formula sheet. One page formula sheet.
Okay.
Okay. So if you want to know more information about how many questions are going to be on the midterm and all, you can take a look at the practice midterm exams shown here. Okay. Other questions, please. So if you send me an email about lab 1 that you want to do your demo later on, that's fine. You can do your lab 1 demo tomorrow as well. Okay. If not, if you have other questions, Zayed, I don't remember your exact email, the content of your email, but we can talk about that in the lab tomorrow. Okay. So the idea is, so far we looked at different applications of OpAmp, ideal OpAmp, inverting, non-inverting, inverting summing amplifier, unity gain, non-inverting summing amplifier. Okay, so we'll come back to talk about more applications, and it may not be possible for me to cover all the material in the class. That's not the intent at all. All the material that you need is on Moodless videos. My lectures are only meant to be a substitute, not a substitute, but a rather additional information. All right, I'll see you folks tomorrow then. Take care.